Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will review everything you need to know about exponentials. So here are two examples of exponential functions. What makes them so is that the unknown, here x, is part of the power. So I'm going to look at graphing these two functions. So you can graph an exponential function using a table of values. So you choose the x values. I just went from -3 to 3. And you substitute in each x value into the equation to get the y value. Now, if we graph y equals 2 to the power of x, I'm going to plot each of these points, so -3, 1 over 8, -2, 1 over 4, and so on. So the graph of y equals 2 to the power of x will look like this. On the other hand, if I were to graph y equals 1/2 to the power of x, it will look like this. So they'll meet here at the point 0, 1. So if we look more generally at the graph of y equals a to the power of x, if a is greater than 1, it has this orientation, and if a is between 0 and 1, it has this orientation. So this was like y equals 2 to the power of x, and this looks like y equals 1/2 to the power of x. So why does it have that shape? So the really important point to understand about exponential graphs is that when a is greater than 1, we have a situation where the y value is increasing at an increasing rate, and here we have one where y is decreasing at a decreasing rate. And we can see that from the table of values up here. So when a is greater than 1, so let's look at what happens to the y value as we go along. So it went up by 1/8, then it went up by 1/4, then it went up by 1/2, up by 1, up by 2, up by 4. Not only is this number increasing, but the gaps between them is also increasing. That's what I mean, increasing at an increasing rate. Similar here, we go down by 4, down by 2, down by 1, and so on. Here, where a is between 0 and 1, we can see that the y value is going down, but the gaps between each number is getting smaller. So increasing at an increasing rate, decreasing at a decreasing rate. We call this exponential growth and this exponential decay. So we're now going to look at examples where a quantity is increasing or decreasing by the same percentage each time. And the percentage in these formula will be R. So it turns out if you increase by the same percentage each time, you have exponential growth, and if you decrease by the same percentage each time, you have exponential decay. Increasing at an increasing rate, decreasing at a decreasing rate. Now these two formula are exactly the same, except there's a plus within the brackets for growth and a minus for decay. So A means the amount you have, whatever the quantity is at a certain time. P is the initial quantity, R is the rate as a percentage, and N is the number of increases or decreases. So you need to be able to take either of these formula and solve for A, P, R, or N. Now solving for A is really easy, you just substitute P, R, and N. Solving for P, the initial amount is easy, you just take A and you divide by this number here. We're going to look now at solving for R and N, and it turns out I have to do both in this question. So the value of my car has decreased by 20% in 8 years. After how long will its value be halved? So firstly, we need to decide, is this growth or decay? Well, because it's decreasing, we're going to use this formula here. So sometimes in hard questions like this, it's worth just writing the formula again and just looking at it, saying, what can I substitute? Now, ultimately here, I want to find n. After how long? Any measure of time involves finding n, the number of times the price has been increased or decreased in this case. So if I want to find n, I ultimately need to know R, P, and A. So the problem is I don't know R, because R is the percentage decrease each time. In this case, it's going to be each year. I need to first find R, then I can substitute R, P, and A to find N. So I'm going to first use this formula here to find R. So we're told the value of the car has decreased by 20% in 8 years. So if I want to find R, I know that we are talking about an 8-year period, so I'm going to make N 8. So here R and N need to be in the same unit. So if I make N 8 years, what I get for R will be the decrease in percentage each year. Now I can't solve for r now, there's too many unknowns, but I do have a relationship between a and p. See, I'm told that the value of the car decreases by 20%. So that means the amount after 8 years is going to be 80% of the original. You decrease the quantity by 20%, you now have 80% of it left. So I am going to replace a here with 0.8p. Now that allows me to get rid of the p. I can divide this side by p as long as I divide that by p. So now I have an equation that has just one unknown. And the r is in just one spot, so I undo what's been done to r in the opposite order to bid mass. So first thing I'm going to do, undo to the power of 8 by taking the 8th root. So 8th root of 0.8 equals 1 minus r over 100. Now to get r by itself, we just undo in the opposite order to bid mass. We subtract 1 from both sides, and then we times by negative 100. Ultimately, we're going to get this 100 times 1 minus the 8th root of 0.8. So we end up getting that r is approximately 2.75%. That means that the value of the car is decreasing by about 2.75% year on year. So now I'm going to use my formula again, a equals p1 minus r over 100 to the power of n. Now I'm going to solve for n. I want to find n number of decreases, how many years until the value's halved. So I can replace r here with my value I just calculated, 2.75. Now, if I want the value to be halved, in this case, the amount I end up with is going to be half of the original. So in mathematical terms, I have a equals 0.5p. So as I did when finding r, I'm going to rub out a, and I'm going to replace it with 0.5p. Once again, that allows me to cross out the p's, dividing each side by p. So, just rewriting this a bit easier to work with, see 1 minus 2.75 over 100 gives me 0.9725. So now I need to solve this equation here. So this is an exponential equation because the unknown is in a power. And when we want to solve exponential equations, we use log. So we simply write n equals log. So the base will be the thing that was being raised to the power, 0.725, and that will be of the other number, 0.5. So this is what logs mean. If you have log of number and number, it means we're saying to what power do I raise this number to get that. So if your calculator doesn't allow you to input the base, then you'll need to use the change. Put in your calculator log. Now this number goes on top in the change of base, 0.5, and then on the bottom it will be log of 0.9725. So you can put that straight in your calculator, and we get about 24.85. So that means it'll take about 25 years for the value to be halved. All right, let's now look more at exponential equations. So this is another example of an exponential equation because the unknown is part of the power. Because the unknown is only in one spot, we simply undo what's been done to it in the opposite order to bid mass. So the first thing I'm going to undo is subtracting 8. I'm going to add 8 to both sides. Next thing I want to do is divide by 4. So I get 9 to the 3 minus 2x is 108 divided by 4. Now, the next thing I need to undo is raising 9 to the power. The way that you undo raising to a power is by using logs. That's their definition. Logs and raising to the power undo each other in exactly the same way as multiplication and division or addition and subtraction. So what I get is the power, whatever was in the power, equals log. So this number is the base. And then this number here is the power goes up here. So The definition of a log is this number to this power equals that. These two are equivalent equations. But now I've got the x's on one side. So if you put log 9 of 27 in your calculator, again, if you can't input the base, you're going to have to put log 27 over log 9. You get 1.5 because 9 to the power of 1.5 is 27. So now this is easy to solve. We simply subtract 3 from both sides and then divide each side by -2. I get x equals 3/4 or 0.75 and I'm done. Let's now look at a harder exponential equation. So this equation is harder because the x is in more than one spot and we have different bases. So the first thing I want to do is make the bases the same, because if the bases are the same, then so too the powers have to be the same. So really, I want to rewrite this right-hand side as 2 to the power of something. So I'm going to have 3 to the power of x minus 2 written like this. So what number goes there? Well, to what power do you raise 2 to get 3? And that's where logs can help us. That will simply be log 2 of 3. So if you put this in your calculator, you might need to do log 3 divide log 2 if you can't input the base. But if you put that in your calculator, you get 1.58496. So that means, by definition of log, this number to this power equals that. It means 3 is 2 to the power of 1.58496. So doing this helps us because now we have the same base on both sides. So we can simply get rid of the 2's. What we're left with now is x plus 3 equals, now the index law says power to a power, you multiply the powers. So I've got to multiply this number by x minus 2. So I've got to multiply 1.58496 by x, and then I need to multiply it by -2. So now we have a linear equation in which x is on both sides. In such a circumstance, you subtract the x, or the pronumeral, with the lowest coefficient. So subtracting x from this side, I just get 3. Now this is 1.58x minus, it's really 1x. So we simply decrease the coefficient by 1, 0.58496x. Now we need to add this number 3.169925 to both sides. So this is an easy equation to solve. 0.58496 is not a nice number, but it's a number nonetheless. The way we undo timesing x by a number is to divide by that number. And so putting that on our calculator, we get x is about 10.55 and we're done. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.